Hello everyone, welcome to my talk, Correlations between Deep Neural Network Model Coverage Criteria and Model Quality. I'm Xiao from Rutgers University. This is our work collaborated with my colleagues Guanhong Xuwei from Purdue University and advisors Zhai, Shiqing, Xiangyu, Zhang from Rutgers, Purdue, and Nanjing University. Deep neural network is becoming part of the new generation of software systems, such as self-driving vehicle systems, computer vision systems. How to guarantee this kind of system quality is an important problem. Just like software testing is a key step in traditional software development, many researchers believe that DNA model testing is critical to model quality and the whole system quality. A very typical software testing lifecycle is shown as following. Given a subject software, various test generation engines can be used to generate test cases. The generated test suite is executed, and the code coverage is measured and provided as feedback to the test generation engine, whose goal is to generate more test cases and can improve the code coverage. The failing test cases are reported to the developers, who fix the corresponding bugs, leading to a new version of the subject software. Inspired by the success of software testing, researchers have proposed DNA model testing to improve model quality. The life cycle of DNA model testing resembles that of software testing. Specifically, the subject becomes a DNA model instead of a program. Model input generation techniques are used to generate inputs. The generation is guided by some coverage criterion, just like in software test generation. A failing input example is the one that causes model misclassification and can be used to retrain the model. The retraining procedure is analogous to the bug fixing procedure, which yields a new version of the model. Code coverage criteria play a critical role in software testing. A large number of coverage criteria have been proposed and used, and different criteria have different levels of strength in disclosing bugs. Inspired by this code coverage criteria, researchers have proposed a large set of DNA model coverage criteria. Specifically, they observed the analogy between activating a neuron and covering a software artifact. Therefore, they propose a number of coverage criteria based on how neurons are activated. Despite the inspiring correspondence between software testing and DNA model testing, there are a few open questions that need to be answered. Specifically, the effectiveness of software testing is built on a basic assumption that while the developers generate more test cases to achieve higher code coverage, more bugs are disclosed and fixed, and the software quality is improved. Although this assumption is largely proved in software testing, its counterpart in model testing is unclear. In fact, the semantics of DNA models is substantially different from the semantics of programs. Intuitively, program behaviors are largely discrete, whereas model behaviors are continuous. Therefore, we aim to learn the correlations between neural coverage and model quality. We studied the correlation from 4 aspects. Question 1. Are DNA coverage metrics correlated with DNA model robustness? Question 2. Is coverage-driven test generation effective in disclosing DNA defects? Question 3. Are the adversarial examples generated by DNA coverage-based testing effective in improving model robustness? Question 4. How are the different DNA coverage criteria correlated? We use 8 commonly used coverage metrics from previous works to measure the neural coverage. Here are the formal definitions of these coverage metrics. Intuitively, NC measures the percentage of activated neurons. QMAC, NBC, SNAC measure to what extent the given set of test inputs cover the main functionality regions and the corner case regions. TKNC, TKNP measure the percentage of neurons that have ever been the top K neurons for a given input set, and the number of different activation patterns for the top K neurons. LSA, DSA measure relative surprise of each input with respect to the training data. To measure the model quality, we use 9 commonly used metrics. Here are the formal definitions of these metrics. These metrics can be divided into 3 categories, which measure the effectiveness of the adversarial attack, imperceptibility of the adversarial examples, and resilience of the adversarial examples to perturbations. Intuitively, MR, ACAC, ACTC measure how often and how confident the generated adversarial examples lead to correct classification results. ARDP, ASS, PSD measure how realistic an adversarial example is in human eyes compared to the original example. NTE, RGB, RAC measure the resilience of the adversarial examples to noise, Gaussian blur, and image compression. For the experiments, we use MNIST, Cephaloton, and ISVHN as our datasets. Some specifications of them are shown in the table. For MNIST, we use 3 pre-trained Lanet family models. For Cephaloton, we use VGG16 and ResNet20. For SVHN, we also use 3 CNN models, and their model architectures are adopted from previous work. We first design experiments to answer question 1. Are DNN coverage metrics correlated with DNN model robustness? We use adversarial example generation techniques to generate a large set of adversarial examples. Given a DNN coverage criterion, we perform input selection to select the adversarial examples that can lead to the most coverage improvement and add them to the training dataset T0 to acquire a new dataset T1. We repeat this step and keep adding new examples to generate datasets from T2 to T10. Here, we measure the coverage value for these 11 datasets. We then perform adversarial training using T1 to T10 and yield new trained models from F1 to F10. We measure these 11 models' robustness. We repeat the whole steps for all datasets and all models. Finally, we perform a correlation analysis for coverage criteria and robustness criteria based on the whole data we collected. This figure shows the coverage value changes with respect to different training datasets. X-axis represents different datasets we generate, and the y-axis represents relative coverage value. From this figure, we can say with new training samples, all coverage metrics are growing. This figure shows the changes of attack metrics with respect to different training datasets. X-axis represents different datasets we generate, and y-axis represents relative attack metrics value. From the graph, we observe that none of them is monotonous. This means adding new samples to improve coverage that not always leads to the improvement of model robustness. This figure shows the correlations between attack criteria and coverage criteria. Each label in x-axis represents one attack criterion, and each label in y-axis represents one coverage criterion. The blue cell means negative correlation, and the red cell means positive correlation. A darker cell or a bigger absolute value means a stronger correlation. Generally, if the absolute value is less than 0.4, it means the correlation is weak. However, if the absolute value is more than 0.7, it means the correlation is strong. This figure indicates that all absolute correlation values between attack criteria and coverage criteria are less than 0.4. This means coverage criteria do not have monotonic relations with model quality. Next, we answer question 2. Is coverage-driven test generation effective in disclosing DNN defects? We use Deep Hunter and PGD to generate test cases respectively. The test cases generated are called DH and DP. We then compare the misclassification ratio and the error infinite distance of DH and DP. To understand how PGD generated adversarial examples correlate with the coverage criteria, we conduct one small experiment. We add 10 images generated by PGD in each single step and calculate the change of the coverage metric value. This table shows the misclassification ratio and error infinite distance for the test cases DH and DP. The average misclassification ratio for DH is lower than that of DP. The average error infinite distances for DP is 3 to 100 times smaller than that of DH. This means that the coverage-based adversarial example generation methods usually have lower effectiveness and add larger perturbations. This figure shows the coverage value change with more samples. The primary y-axis shows the percentage for ratio values, and the second y-axis shows the value for TKNP. The lines for criteria except TKNP grow rapidly at the beginning and then plateau afterwards. This means adversarial examples may not necessarily increase the coverage, but TKNP shows an almost linear relationship with the number of new samples. To further study this, we calculate the growth of TKNP when we add benign samples. This figure shows the TKNP value change of benign samples and adversarial samples. From the figure, adding new benign samples and adding adversarial samples have almost the same effects to TKNP. This means TKNP cannot distinguish the differences of benign samples and adversarial samples. Then we conduct experiments to answer question 3. Are the adversarial examples generated by DNA coverage-based testing effective in improving model robustness? We first retrain the models with coverage-guided testing and get model FSE. We then retrain the models with PGD-based adversarial training and get model FA. Finally, we compare two models' accuracy on benign samples, adversarial samples generated by coverage guidance, and adversarial examples generated under PGD attack. The table shows model accuracy under different scenarios. The second column shows the retrained models. For each model, we show the accuracy on benign samples, adversarial samples generated by coverage guidance, and under PGD attack in the third to the fifth columns. In each cell, we also show the model accuracy as well as the difference compared with the original model. To compare the robustness improvement of the models retrained by coverage-guided testing and adversarial training, we generate a brief table from the original result table. This table indicates models after coverage-based training are more vulnerable than those trained by adversarial training. This means coverage-based training is not effective in improving model robustness compared to adversarial training. We finally design experiments to answer question 4. How are the different DNA coverage criteria correlated? Here, we reuse the design and the data from question 1, but analyze the data from a different angle. This time, we only analyze the correlations between different coverage criteria. The results are shown in this figure. All labels in x-axis and y-axis represent the coverage criteria. From the figure, absolute correlation values between some criteria are larger than 0.4. The absolute correlation values between 3 criteria are larger than 0.7. This means most DNA coverage criteria correlate with each other, and some have strong correlations. Through our study, we found DNA coverage criteria do not have monotonic relations with model quality. Although DNA coverage criteria can be used as guidance to find adversarial examples, effective adversarial examples may not lead to higher code coverage. Existing methods used to generate adversarial examples based on coverage criteria usually add larger and human visible perturbations compared to existing gradient-based methods. Using such inputs in model testing is analogous to having program inputs that may violate the software input preconditions. Adversarial examples generated by DNA coverage-guided methods can be used to retrain a model to improve model robustness against the adversarial method used to generate the training inputs. However, such models are not robust against gradient-based attacks, such as PGD attack. Most existing DNA coverage criteria correlate with each other, some having strong correlations. This helps explain their similar behaviors in all experiments. However, it's unclear whether there exists partial order among them, like code coverage. Before the end of my talk, I have some points of view to share. Coverage criteria have effectiveness in some situations, such as adversarial training. But the correlations between existing coverage criteria and model robustness are not very strong. So how can we propose better coverage criteria that show very positive correlations with DNA model robustness? This problem deserves more attention from our community. Based on the feedbacks from reviewers and many other researchers, we believe that our community shall establish a set of standards for evaluating future proposals in DNA testing. They shall include testing various model properties and cover various model architectures and tasks so that the results can be comparable. Our datasets and codes are available on GitHub. Please feel free to play around with it. And as an initial step of what we just discussed, we are building a repository to help our community evaluate future proposals. It will include our work and artifacts from other related works. Any contributions from our readers are welcomed. Finally, it's my honor if you can help us spread our work. Thank you.